We have the smart sensor sitting here on the sensor module, and what we've got here is an interface, LabVIEW interface, that'll show you the raw signal responses from our nano sensor array. And right here you see there are 16 nanosensors with 16 signals. We've got a temperature and a humidity sensor that are on board to the chip. And if you zoom into that chip, what you're really looking at is a cutaway of the chamber, the sampling chamber, and you've got the MEMS sensor is in the middle with all the bond leads, and then you've got an onboard temperature humidity sensor that's fed back into our algorithms. And then underneath we have a EEPROM that has specific information during manufacturing that goes with every smart sensor. So what I'm going to show here is a demonstration of the smart sensor system detecting toxic industrial chemicals and showing the strength of this approach, where we have negation sensors that will help proactively look for and negate possible interferent conditions such as relative humidity. And every technology has its own vulnerabilities, and we'll show you how we've addressed it in ours. And in reality, other technologies either haven't addressed it or they couldn't address it because the interferent masks their signal's ability to pick up the actual threat gas. So what I have here is ammonia gas. I'm simply going to open up the supply, put the sampling tube into it. You're going to immediately see responses from the nanosensor arrays. These are instantaneous responses. These sensors all go feed into a suite of algorithms. And if we go to the output of the algorithm, before we did the hit, there is no gas detected. It takes up to at least 12 seconds to identify what gas. We detect ammonia at 3.5 parts per million. If I go back to the raw signal, you can see that they are actually responding. I will disconnect. So I'm now removing the ammonia, and you will see that the raw sensors will immediately recover. It's a reversible behavior, and these sensors will last for multiple years, typically 4 to 6 years. If we look at the humidity sensor, we actually can see that while we were exposing it to 3.5 parts per million of ammonia, we were actually also experiencing a simultaneous change in relative humidity of over 25,000 parts per million, or about 25% RH. This is simultaneous, and we were still able to detect the actual trace level threat in that simultaneous RH change. This is significant. Most technologies cannot do this. Even if they had an onboard temperature humidity sensor, the RH change would have masked their signal response to the threat. So if I go back to the gas details, we have recovered. So now the device says there's no more threat, and it is ready to test to another condition. If we take RH, so this is simply water in a bottle, and we disconnect and sample through our sensor array, we'll see some instantaneous responses to the moisture change. We'll see that also as evidenced on the humidity sensor. But the key here is with the negation sensors is we could say, okay, we don't detect the threat, but our technology, the uniqueness is we will proactively identify threats, non-threat conditions, as in this case relative humidity, to tell the algorithm we've identified something, it's not a threat, so we've negated that possible false alarm. I disconnect, and at this stage you can see that the nanosensor array is in full recovery mode, the humidity sensor is in full recovery mode, and what's critical about the humidity sensor's responses to both the ammonia plus RH change and then the RH change only is they're actually identical from an RH sensor standpoint. But the nanosensors are absolutely not identical. You have some sensors that will respond to the ammonia, but they don't respond to RH. That would be evidenced by, for example, sensor 1. And then also if you look here at sensor 4. And then if you even look at a sensor 6, the ammonia response was quite large. The RH response only was quite small. And again, the ammonia response was to about 3.5 parts per million. The RH change was about 25,000 parts per million. So now if I go back to the algorithm output, we're back to no gas detected. If I go back to the raw signal data, you'll be able to watch. I'll expose this to chlorine gas. Again, I'll take the sample inlet, connect it to our chlorine source. If we look, we get immediate nanosensor array responses, and these are growing. So these rates of responses are what information is fed into the algorithms. Again, we see an immediate RH change simultaneous to that. It's a very difficult condition. And we go to the algorithm and we detect chlorine within seconds. And if we go back to the chlorine responses, they're still responding. If I remove them, they will start to recover. So I have now disconnected. This is the sample inlet. We are now in recovery mode. And as evidenced, if you look at sensor 5, it's immediately recovering. And if you look at the RH responses for all three conditions, they look identical. And the essence of this is the smart sensor can detect chemical threats at trace levels, even not only in the background of interference, but in simultaneous changing backgrounds with interference. And RH is a universal interferent to all technologies. And if we go back to the gas details, we are back to no gas detected. This is fully autonomous. It's continuous, real time. We do, just to look, we sample gas in, comes through our sensor, through a pressure or a flow sensor, through our pump, and exhausts out this way. This is a fully autonomous system with no user interface, a user intervention required, and we simply have an on-off power switch, and there is no calibration required for detection or identification, and only periodic calibration is suggested depending on the level of quantitative accuracy that's required by the user. And so now you can see we go to our algorithms. We are good to go. We are good to go here. I will just show you again ammonia. If we expose the device, the smart sensor, back to ammonia, we are now sampling ammonia. We see instantaneous responses again. We also see instantaneous humidity response with the humidity sensor. And if we go to the algorithm and we await the assessment, the algorithm is taking in this raw data and tells us that we in fact have ammonia. It's important to note that the concentration is slightly less this time, and that actually makes sense because this bottle builds up headspace and to build up concentration, and we had just sampled from it before, so it was building back up that headspace. We disconnect. We are back to recovery, and the recoveries are quite rapid, and the humidity is recovering as well. And it's also important to note that the humidity sensor does not respond to the chemical threats. It's a very selective and specific humidity sensor, coupled with our nano sensor, provides all the information you need, not only to identify the threat, but to identify it in the presence and against humidity changes. If we go back, we have no gas detected.